Hi, I'm Kent, and today I'm going to show you two tools in LabOne Q that will help you visualize your experiments before you've even connected to your instruments. Let's dive in and get started. What I have prepared is a Python notebook that's also on our GitHub that follows along with our section chapter. Here's the link. It's in our LabOne Q user manual, sections and pulses, and in the introduction, there's a link to our GitHub page, and here's this section tutorial. I'm only going to be talking about the beginning of it today. What you're going to start with is we'll import the LabOne Q functionality, and then two tools, the plotting tools and the interactive pulse sheet viewer that we'll use later on in this little demo. So let's import those. The device setup and driveline calibration, I'm not going to be talking about it at all today. We'll cover those in a separate video. I want to talk about the meat of the what most people will spend time on, which is their experiment. So what I have defined here is a single Gaussian pulse of length 100 nanoseconds and a driveline which will play the pulse on. In the experiment itself, we have a single so a single count real-time loop. Within that, we have a section. That section is 2 microseconds in length, and in that section, I'm playing this pulse I've defined earlier. Today, I'm just using our offline emulator here, so you don't even need to have the instruments available. Maybe your colleague is using them in the lab. Maybe you can't get into the lab that day, but you want to check if your experiment will compile correctly, if all of the timings line up of your pulses. So we can run that. Now we have our compiled experiment. And now what we can do is we can plot this compiled experiment in our output simulator. There we go. What we have here is we have our single Gaussian pulse and our 2 microsecond long section. We can see that if we want to zoom in on this pulse, we can set the start time. Let's keep it at 0 for now, and the length. And let's say I want to look at 120 nanoseconds of this. There I can zoom in on the pulse. What we can also do is use this interactive pulse sheet viewer, also taking the compiled experiment as an argument, to get a similar view. This is a bit more of a cartoon, but with a ton of information. So what we have here is the global timing, the sections, and here the section names and the pulse names are what you've given in the above experiment. That can be really useful as your experiment grows. If I click on my pulse here, I can also look at its timing, looking at the signals here, and I can look at all of the events as well as their sample equivalent timing there. If I would rather look at this in a browser, then I can make inline equals false here and open this in the browser. I have all the same information. I can click on the pulse and I can look at the events. Coming back here, I have to stop this hosting, and I could even save my pulse sheet. I'll just give it a name, my saved pulse sheet, and the compiled experiment again. This generates an HTML file that you can open in the browser. This doesn't have the same pulse information if you click on the pulse itself, but all of the other information is present. So this can also be really useful as you're generating lots of experiments to save these as you go. And we can also, so for one pulse here, let's look at some other things we can do with this that are useful. Here I have the section alignment aligned to the left. This plays the pulse at the very beginning. Let's see what happens if I set this to the right. So we'll run this, recompile. I'll take out the length argument here. And now I've moved the pulse to the very end of the section. Now the pulse is played at the very end. And in the pulse sheet viewer, we'll look at the interactive pulse sheet viewer again. And now I see, just as well here, that the pulse is all the way to the right of the section. We can add more pulses. So here I can add delay between the pulses. We'll add it on the same signal line, the drive line, and we'll give it a time of 5 nanoseconds. Then after that, I'll play the same pulse, also on the drive line. We'll compile again. And now we see the pulses appear one right after the other with a short delay between them. A bit hard to see with the pulse sheet viewer, but again we can, with the simulator default, but we have lots of arguments we can give it. We can zoom in. So let's give this a length of, let's say, 200 nanoseconds. Now we can zoom in and see the spacing between the pulses. Similarly in the pulse sheet viewer, with these two pulses here, I can hover them, move them around, scroll in, click on one of them, click on the other and see their relative timings, and check out all of the details of the events. Now, as your experiments grow, this is relatively simple, but it can be increasingly difficult with many pulses to figure out the relative timings. Let's take, for example, a quantum error-corrected surface code. So this is a surface 17, meaning 17 qubits. In one quantum error correction cycle here, we have many different control pulses, readout pulses, lots of things overlapping. It can be very, very difficult just from inspecting the code to understand if you've done everything right. So now what we can do is we can run in the pulse sheet viewer and inspect the relative timings visually. This is really nice. So for example, for our X stabilizer, we can see all of its contents. We can scroll in and see what names we've given the sections. I can click on an individual pulse again and see that my Y pulse here has the correct timing that I would expect. And I can look through all of the individual events down to a single sample and see that things are played where we want them to be. That's all I wanted to show with visualization in LabOne Q. Thanks for watching.